Assalamualaikum and good day all. So today we will continue on the chapter 3, which is application of differentiation. So we will apply all the rules that we have discussed previously. And this is the overview for this week topic. First is the rates of change. Second, gradient of curve at a point. And third is the local and absolute extremum. So all these three topics will be split into two parts. Okay, and these parts I will discuss the rates of change and gradient of curve at a point. So the learning outcomes for today is first to calculate the rates of change of a variable if the rate of change of a related variable are known. Okay, and second is to find the gradient of curve at a point. Okay, let's start with the rate of change. Okay, suppose we have, if y is a function of x, then we will have dy dx is the rate of change of y changes with respect to x. In application, rates of change must be accompanied by appropriate units. In general, the units for a rate of change of y with respect to x are obtained by dividing the units of y by the units of x. Okay, let's consider one example. If y represents a displacement in meters and t represents time in seconds, then dy dt is the rate of change in y with respect to time t with units of meter per second. Okay, and we write as meter per second here. Okay, and we have example B. If theta represents a temperature in degrees Celsius and L represents length in centimeters, then a rate of change of theta with respect to L, that is d theta dl, has units of degrees Celsius per centimeter. We have degrees Celsius per centimeter. Okay, now we will use the differentiation in this example. So example 1. The area of an ink blot at time t is a centimeter squared, where a is equal to 3t squared plus t. Okay, determine the rate of change at t equal to 5. So we have the keyword here is rate of change. Okay, so to find the rate of change, so what we need to do is from the area given, okay, the area is a equal to 3t squared plus t. So what you need to do is to find the rate of change, which is dA per dt. Okay, which means that you need to differentiate a with respect to t. So differentiate 3t squared, so you will get 60. And differentiate t, you will get 1. Okay, so this is the derivative, or this is the rate of change. Okay, the question asks you to determine the rate of change at t equal to 5. So what does it mean? So what you need to do is to substitute the value of t here with 5. Okay, so you will have 6 times 5 plus 1 is equal to 31. Okay, so the rate of change at t equal to 5 is 31. Okay, and if we have we put the units, so we have the rate is 31 centimeters squared per second. Okay, let's look at example 2. The radius r centimeter of a sphere at t seconds is given by r equal to 4 plus 3 over 2 plus t plus 2t squared. Okay, A, find the initial radius of sphere. B, find the rate of change of r at t equal to 3. So how are we going to solve this example or this question? So we have the equation of r. Okay, the given r is 4 plus 3 over 2 plus t plus 2t squared. Okay, question number 1 is to find the initial radius of the sphere. Okay, so to find the initial radius, so what you need to do is just find initial radius means we have at t equal to 0. So at t equal to 0, so r0 is equal to 4 plus 3 over 2 plus 0 plus 2 times 0 squared. Okay, and solve this one. So you will have 4 plus 3 over 2, which is equal to 11 over 2. Okay, so we need to write the units. So the unit is centimeters. Okay, so the answer for A is 11 over 2 centimeter. This is the initial radius of the sphere. Next, we move to second question. Okay, find the rate of change of r at t equal to 3. Okay, we have the equation r just now. Okay, the question asks you to find the rate of change, which means that we need to find dr dt. But before we find the dr dt, okay, look at the equation. So we have a fraction here. Okay, so we can rearrange or rewrite, not rearrange, we rewrite the r equation as 4 plus 3, okay, and put 2 plus t top, okay, plus 2t square. Okay, so we have the r function here. Okay, next is to find the rate of change, means that we need to find dr over dt. Okay, differentiate 4, we will get 0. Okay, and differentiate 3 times 2 plus t to the power of negative 1. So we will have here plus 3. Okay, and then we have this one as negative 1. Okay, just bring the negative 1 in front. So we'll have negative 1. Okay, put the in bracket 2 plus t. Okay, and this one will be to the power of negative 2. Right, and you need to multiply with the derivative in the bracket here, which is if you differentiate 2 plus t with respect to t, you will get 1. Okay, and next, okay, we have 2t squared, so differentiate, you will get 40. Okay, so next, simplify. Okay, so you have 3 times negative 1 times 1, so you will get negative 3 over 2 plus t squared plus 40. Okay, so this is the rate of change. And the question asks you to find the rate of change of r at t equal to 3. So what we need to do is to substitute t with 3. Okay, so substitute with 3, so you have negative 3 over 2 plus 3 squared plus 4 times 3. Okay, this one you will get 11.88 centimeter per second. Okay, the unit is centimeter per second. Alright, okay, now we proceed to example 3. So the radius r of a spherical balloon at time t seconds is given by r equal to t squared plus t. Okay, express the volume of the balloon v centimeter cube in terms of t and find the rate of change of the volume at t equal to 4 seconds. Okay, the first question is to express the volume in terms of T. And the balloon is a spherical balloon. So the volume of the spherical balloon we can write as V equal to 4 over 3 pi r cube. Okay, but this is in terms of R. Okay, we need to write V in terms of T. So given to you the equation of R, which is equal to T squared plus T, so we substitute R here with T squared plus T. Okay, we have the new function there, V equal to 4 over 3 pi, okay, T squared plus T to the power of 3. So this is the volume. So next is to find the rate of change of the volume. Okay, so the rate of change of the volume is dV dt. So which means that we need to differentiate V with respect to T. Okay, so just use the rules like the previous example where we will get 4 over 3 pi. Okay, and we put 3 in front. So we have the term in bracket T squared plus T, and the powers will reduce 1, so we have here to the power of 2. And differentiate the term in bracket, which is we will get T squared, differentiate you will get 2T, and differentiate T you will get 1. Okay, we close the bracket, simplify it, so we will have here 4 pi okay, T squared plus T squared times 2T plus 1. Okay, so this is the rate of change. So at T equal to 4, so we can have dV dt is equal to 4 pi. Okay, we substitute T with 4, so 4 squared plus 4 squared, so 2 times 4 plus 1. Okay, so this one you will get, the answer is later you will get 14,405 centimeter cube per second. This is volume. Okay, so we now discuss the next subtopic, which is constant rate of change. Okay, we have the keyword here, constant, so which means that we have just a number. Okay, let r centimeter be the radius of a circle at t seconds given by r equal to 12 minus 2t, where t is between 0 to 6. Okay, thus the rate of change of r with respect to t, or we write as dr dt, is equal to negative 2. Okay, if we differentiate r with respect to t here, okay, if we differentiate r with respect to t, so you will get negative 2. Okay, and this is a constant value, okay, which is also known as constant rate of change. Okay, it means that for every value of t, which is from 0 to 6, so dr dt is always the same. Okay, hence, the constant rate of change is given by dr dt is equal to changing value of r divided by changing value of t. So let's proceed with example 4. Okay, the radius r centimeter of a circle increase at constant rate of 0.5 centimeter per second. Okay, if the initial radius is 3.5 centimeter, find the radius of the circle after 10 seconds. Okay, how to solve this? Okay, given to you at a constant rate is the dr dt. So we have dr dt is equal to 0.5. Then we have dr dt is the changing value of r divided by changing value of t. So we have just now the r dt is 0.5, and we have changing value of r is the initial value is 3.5. Okay, so the new value we do not know, so we just let it as r. So r minus 3.5 divided by 10. Okay, because after 10 seconds, which means that the changing value of t is equal to 10. So we will have, if you solve the equation there, so you will get r equal to 8.5 centimeters. Okay, next subtopic is related rates. Okay, consider the example below. When air is being pumped into a spherical balloon, the radius of the balloon increases as the balloon expands. Okay, and the rates of change of the radius r and the volume v at time t are dr dt and dv dt. Okay, we have two rate of change now. Okay, r respect to t, r is radius, and v volume respect to t. Okay, and at first we have the volume of sphere is 4/3 pi r cube. Okay, since v and r related by the formula v equal to 4/3 pi r cube, okay, the rates dr dt and dv dt are also related. So that's why we have the related rates there. And this relation is obtained by the formula dv dt is equal to dv dr times dr dt. It's the same as the chain rule that we have discussed before. Okay, thus the problem involving the rate of change of several related quantities is called the related rate of change problems. Okay, if we have a few variables or several quantities, so we call as related rate of change problem. Okay, in general, if y is a function of x, the problems involving the rates of change of y and x can be solved by using the chain rule. I just said just now, so this we have discussed before. Okay, we have dy dt is equal to dy du times du dt. Okay, let's look at this example, example 5. The radius of circle is increasing at the rate of 5 cm per minute. Find A, the rate of change of the area of the circle when its radius is 12 centimeters. B, the radius of circle. Find the radius of the circle when its area is increasing at a rate of 50 pi centimeters squared per minute. Okay, let's A first. So given in the question, the radius of circle is increasing at the rate of 5 centimeters per minute. So we can write these terms as radius dr dt equal to 5 centimeter per minute. Okay, so the first question is to find the rate of change of the area of circle. So we need to have the formula for area of circle. Okay, which is equal to what? You still remember? What is the area of circle? It's this pi r squared. Okay, so rate of change. What we need to do or what we need to find is the dt. Is this one is equal to dA, since in our equation we only have r, so we have dA dr times dr dt. Okay, so dA over dr is from the formula of A here. Okay, this one is A equal to pi r squared. So differentiate pi r squared, you will get 2 pi r. Okay, and we have dr dt just now, okay, given in the question, which is 5. So we just substitute the value of 5 there. Okay, and since the question asks you to find the rate of change of the area of the circle when its radius is 12, which means that you need to find dA dt at at r equal to 12. Okay, so substitute r equal to 12, so you have dA dt is equal to 2 pi times 12 times 5. So you will have the answer is 120 pi centimeter per minute. Okay, so this is the answer for question A. Okay, let's proceed to question B. Okay, we need to find the radius of the circle when its area is increasing at the rate of 50 pi centimeters squared. Okay, again, we have the formula dA over dt is equal to dA over dr times dr over dt, and this is circle, so we have just now the formula for circle is pi r squared. Here we have differentiate a respect to a, so we get 2 pi r. Okay, and dr dt just now is 5. Okay, here the radius of the circle when its area is increasing at the rate of 50 pi centimeter per minute is the dA dt, which means that we have here as 50 pi. Okay, so when we solve this one will get 10 pi r is equal to 50 pi. Okay, therefore we have the radius is equal to 5 centimeter. So this will be the answer. It is the radius of the circle when its area is increasing at the rate of 50 pi centimeters squared per minute is equal to 5 centimeters. Okay, we proceed to example number 6. The volume of a constant height cone is decreasing at the rate of 4 centimeter cubed per second. Find the rate of change in its cross-sectional radius when the radius is 5 centimeters and the height is 8 centimeters. Okay, again this one we need to find the rate of change. Okay, but we need to have the function first. Okay, the keyword in this example is volume of a constant height cone. Or we have actually the volume of a cone. V. Okay, what is the volume of a cone? Still remember? Okay, the volume of a cone is 1/3 pi r squared h. Okay, so this is the volume of a cone. Okay, so the volume is decreasing at a rate of 4 centimeter cubed per second, which means that we have another information, which is dV dt is equal to -4 because it's decreasing. Okay, So we have the question asks to find the rate of change in its cross-sectional radius. Okay, so we have by using the chain rule, okay, we have dv dt is equal to dv over dr times dr over dt. Okay, where we have dv dt given in the question is equal to -4. Okay, dv dr, okay, we can find it by differentiate the volume of cone respect to r. So differentiate 1 over 3 pi r squared h, so we'll get 2 over 3 pi r h. So this is the volume here. Okay, and we have dr dt. So actually this is what we want to find. Okay, this dr dt that we want to find. Okay, and therefore, okay, solve the, this is just algebra. So dr dt is equal to what? -4 times 3 over 2 pi rh. Okay, given to you the radius is 5 and the height is 8. So just substitute it, so you get -12 over 2 pi, r is 5 and h is 8. Okay, right, so if you just use your calculator, so you get -0.0477 as the answer. So this is the rate of change of the radius. Okay, so the radius is in centimeter, so rate of change is just centimeter per second. Okay, so the answer just now you get negative, so it means that it decreasing at the rate of 0.0477. Okay, so this exercise I want you to try to answer it, and I have given the answer to you, so please try. Okay, so now we comes to second part, which is not second part, it is second subtopic in the first part, which is gradient of curve at a point. Okay, the gradient of a curve at a point can be defined as the gradient of the tangent line at the point of the curve. Okay, so we have this curve. This is the curve. Okay, so this is the curve, and the tangent line, this is the gradient of the tangent line. So this is T. Right? So by referring to the graph, okay, assume that PT is a tangent to the curve at P. Okay, let P be a point moving along the curve AB. So we have a P here, it's moving along the curve AB. Okay, when P is moving from A to B, the tangent to the curve is also moving. So here, in other words, the gradient of the tangent to the curve is changing, and it can be obtained by substituting the coordinate points in dy dx or f prime x. So let's say you have the point here, you have the point P here. Okay, this is point, so this will be the tangent. Okay, if you have this one, this point, so maybe this is the tangent. Okay, let's look at example 8. Find the gradient of the curve y equal to x cubed plus 8x minus 5 at the point 2, 19. Okay, for the solution, so given the equation as y equal to x cubed plus 8x minus 5, so we need to find the gradient, which is dy dx. So differentiate y respect to x, so you will get 3x squared plus 8. Okay, and when x equal to 2, because we want to find at the point 2, 19. Since we have the equation in terms of x, so we need to find the dy dx at x equal to 2. So solve it and you will get 20. Okay, so the gradient is 20. Okay, let's proceed with the last example, which is example 9 in this first part. Okay, find the equation of the tangent to the parabola y equal to x squared minus 5x plus 3 at x equal to 3. Okay, first thing that you need to do is to differentiate y respect to x. So you have dy dx equal to 2x minus 5. So at x equal to 3, the gradient of a curve is equal to 1. Okay, this is by substituting the value of x with 3. Okay, so you have 1 here. So this is the gradient of the curve. Okay, so for example, this is a parabola. Okay, we have something like this is the parabola. So the gradient, okay, is actually the gradient is 1, which means that you have positive 1. So somewhere like here, okay, so this is the gradient. So here you have dy dx equal to 1. Okay, and this one at x equal to 3. Okay, so this is the tangent, so dy dx equal to 1. Or if you still remember the linear equation, y equal to mx plus c, so this one is actually the slope. Okay, so the question asks you to find the equation, okay, not the gradient. So you need to find the equation of the tangent to the parabola at x equal to 3. So what you need to do is, first we need to know the value of y. So how are we going to find the values of y, or the value of y? So by substituting x equal to 3 in the equation. Okay, so if you substitute x equal to 3, so you have y equal to negative 3. Okay, by using the linear equation formula, okay, we can have the equation as y minus negative 3 equal to 1 x plus 3, and rearrange that, so you will have y equal to x minus 6. So this is actually comes from, you have y minus y1 equal to m x minus x1. Okay, or if you just want to use this formula, y equal to mx plus c, so we have the value of y, we have the value of m, and we have the value of x, so we can find the value of c. So y now is negative 3, our m is 1, x is 3. Okay, so plus c. So now our c, you can have c is equal to negative 6, and therefore we have y equal to m is 1, so just x minus c, just the same as here. Okay, so that's all for the first part, so we will continue on second part later. Thank you.